All right. Well, I mean, like, this is the last session. Okay, well, let's relax, everybody. Okay, it's going to be short, hopefully. And I know, I mean, like, how many sessions we had today? Pretty amazing, right? So for today, I think, like, one of the things I thought about, talking was almost doing a 101 course in what I call spatial modeling. I think, we've heard a lot about, like, new data, new ways of using location intelligence. I wanted to go a little bit more to the fundamentals. So I know it might not be the best for, ending, a session. So stay with me, and we're going to be, shouting in the middle of the presentation so that we all stay awake, okay? And we're only like a few minutes away from a beer, so it might help. All right, so we'll start, with, I'm going to start, by explaining something that might not be so obvious. What is the difference between knowing where and knowing why? I'm going to try to show you why in our industry we've been traditionally very good at actually, seeing where things are, but not necessarily understanding why they are there. So let's put the two examples. So the first one. So the classical way that we use maps is where I'm selling more my product. This is the classical thing that you do on BI. I just want to put, points in the map. I just want to see where there's more customers, where am I selling more, right? So that is what we call very much, descriptive analytics. It's just about seeing what you couldn't see in an Excel. It's very powerful because you can see in the map, you can actually start getting an idea about something is happening somewhere, right? But if you actually really want to ask why, the question is can we model the characteristics that demonstrates, that helps me understand why my product might be more susceptible to be sold on that location? That's a much more elaborated thing. It's not about saying I'm selling more here, it's that I understanding why I am selling more in that particular place. Second one, where do we find higher than expected proportion of traffic accidents in a city? Very classical, heat map, you see, wow, that's a hot spot. Let's try to avoid it. But the real question is really why is that happening? What are the factors that, contribute, so that there's more accident in a particular location? And even more, is there policy changes that could be done that could potentially reduce that number of accidents? That's the very big difference between one or the other. And unfortunately, for most of us, we're still on the left side. We're still, talking about where things are happening and not on why they're happening there. So we're going to go a little bit more towards a little bit of, statistics in here. So, and to that, I want to introduce it, we're coming to an era where, guys, making maps, we all love it, but we have to go beyond that. We already all know how to make a map. We have to move from visualizing data on maps to really analyzing data using maps, okay? So that's the core of what I would like you guys to get out of here. That, now we have the power to start understanding what is the underlying structures of the data that will help you to go beyond just seeing the things, but understanding why they're there. So, and for that, and that's why I call it, Spatial Modeling 101. It looks like a Friday, 6 p.m. at university. Really, really great way to call start 101. But I don't know how many of you know Tobler's first law of geography. I think there's a bunch of geographers in the room. How many geographers do we have in the room? Yeah, great. Oh, that's a lot. Okay, so yeah, that's something that we know very, very well. And it's actually, it's pretty simple, but at the same time, it's really powerful, as you will see. So essentially, it says that everything is related to everything else, but near things tend to be more related than distant things. It's kind of obvious, but it's very powerful from a statistical, from a mathematical perspective, the kind of things that we can do if we make this assumption. And I'm going to go into that. By the way, Tobler passed away last year, so if you're a geographer, I think, this was the guy that started geostatistics, so very, very, we always have to feel very, honored, but no, I just want to say, thankful for, his contribution, which has been tremendous to this space. All right, so how does this work? So, well, the first thing is that, you might wonder, is it really my business spatially dependent? Is it a customer close to another customer actually more related than a customer that is farther away? That is a very legit question. You have to start by asking that. And the cool thing about it, I'm going to go very simple in some of these things, is that we have a lot of geostatistics that can help us on this. So First one we call is more an index, more an I, very mathematical. Again, stay with me. It's pretty easy when you get the concept. So this is an index. This is a number that goes from 1 to -1. And essentially tell us, like the spatial structure of your data. So think of a data set that will look like a +1, is where you can see an incredible structure of clustering of the data. So you can see that all your customers are in one location and they are close to another, and then there's no others, and then they're suddenly all together again, right? So when they're very, very clustered, in a maximum, think of it like if it was half and half, then that will have like 1. So obviously, when you see it on the map, you see there's some structural relation. There's some parts in the world where, like I see more, and in others that I see less, right? The opposite is also very interesting. It's what we call negative spatial correlation. Think about like a chessboard, right? Where you see like the pattern of it actually is exactly, totally the opposite. There is no like clustering at all. In fact, actually, it's the less disorganized that you could be. That's what we call a negative spatial correlation, and that will be -1, which is also very useful. Because if you know that your customers never cluster together, you also know where they will be. So you see, so both sides are very good for prediction. The problem is when you're like in the middle, when there's no like a spatial structure in your data. That actually what it means is that like location is not fundamentally to the business problem that you are analyzing. That's what we call something on the 0, it goes invariant. And in reality, this is the first thing that we check. If your data does not have a spatial structure, and more an index is in this area, probably you shouldn't be doing a spatial analytics, and we wouldn't probably help you. Now, the good thing is that most of the things that that happens, like have some spatial relation. We hear a lot like everything happens somewhere. So it's most often you will find some spatial relation, and most often the problem is that people are not taking it into consideration. So now we're going to talk about like, let's say that now we see that actually our customers, our problems are spatially related, right? So how do we use that, right? So, So think of it as the spread of a virus, right? So think about like the Ebola outbreak in 2014, right? So this is very, very obvious. Remember the first law of geography. Things that are close by tends to be more related than things that are far away. In this case, it's very obvious. If you're closer to where the Ebola started, it's more likely you have a higher chance of getting Ebola too, right? So the farther away, the less likely. To a point where if you're in Spain, fortunately, well, actually that was a bad example. If you're in Holland, Spain, we did get some Ebola, but you actually do not get affected by it, right? So that's the idea. That's very obvious. Everybody understands how viruses spread, right? So the same thing really applies to customers. So think about setting up alarms. If your neighbors buy an alarm, if your neighbors are all having alarms, the likelihood that you will buy an alarm increases, massively. Why? Because fear is also probably very viral, right? But because we have influences, right? So again, this is the first law of geography there. If I'm the only house there with no alarm, the probability that you can sell me an alarm there is much, much higher if there were no other alarms on the area, right? That's super powerful if you can mathematically model that. And that's what we do when we do a spatial modeling. So that's the first characteristics. Knowing what the neighbors around you have, helps you to determine the likelihood of you going that way. So the way actually this works mathematically is we create these so-called decay curves. Right? It's a little bit more complicated, but think of it like a way to measure a spatial autocorrelation. So stay with me. This is very simple. So if you're very close to to your neighbor, the impact that your neighbor has on you is very, very high, right? But the farther that you go away, the impact starts going less and less and less until if the one that you talk about is 10 kilometers away from you, now it does not have any effect, right? So you define these curves where essentially it says your people close by has a lot of impact until a point where it's not relevant anymore. But those curves can change. So it might be that, everybody around 5 kilometers around you has a lot of impact, right? And then, whoop, the influence starts decaying really, really fast, and then there's no effect anymore. Or it can be linear, right? So those are the type of relations that we put on the models where we understand that, this is the impact that this point has in this other point, right? This is how we model it internally. Super powerful, Now, the second part, and this one, I really like it. It's another point, that derives from the same first law of geography, is that the impact does not have to be the same everywhere. And this is, I'm going to use, like one data set that I would like. We will probably tweet it later, but there's this really interesting analysis done in Stanford, where essentially they analyze all the solar panels in the United States, all the locations. Remote sensing, they found it, so now they have all the solar panels installed there. And one of the things that they found is that, well, what we know, if all your neighbors install solar panels, it's very likely you will end up also buying solar panels, right? But it's actually, they found that if 10% of your neighbors already have solar panels, the sales of solar panels skyrocket. So it's the first 10% that is really hard to get, and then after that, sales boom, right? So they found that in most places. But they found that in other neighbors, actually, they need to be 20%. So only when you got like to 20% actually houses with solar panels, then it skyrocket. And that was, and the most interesting that they found, is that the biggest kind of like reason that could explain it was inequality. Essentially, how much was the inequality of the neighbor? The more inequality it was, the bigger the amount of solar panels you have to have in order for it to skyrocket, right? Which is interesting on its own, but this is the one I love the most. It's the last session, and here I'm putting a picture of a Spanish philosopher, right? Which is Ortega y Gasset. For those who are in Spain, you might know, is one of probably the most famous philosopher in Spain. And he has this famous quote which says, "Yo soy yo y mis circunstancias," right? I am myself and my circumstances. In the context that no one is an island. We are all influenced by everybody else, right? So here you have like a philosopher essentially describing the first law of geography, right? So essentially saying like you are influenced by the surroundings, by like your circumstances, where you live, right? The environment in where you behave. And how does this actually work going into this one? So if we look back at like the solar panel, imagine like two customers. Customer A and customer B. Same income, same house, same status, same number of solar panels around them. All the things that we talk about will not necessarily mean that they have the same probability to buy a panel. And why? Because that impact that we were talking about, like the influence that we have one on another, changes from place to place. Let me put another example I didn't want to put in the slides. If you earn a certain amount of money, and you have a certain amount of kids, and you have that certain type of house, and you live in Pozuelo, and another one lives in Coslada or another neighborhood in Madrid, the likelihood of buying a Tesla is different. It's not only about how similar two persons are, but also how different their surroundings are. So the neighborhood where they live also influence. Even if you are exactly the same person, you will act differently depending on the context that you live in. And that means that you cannot have a model that will explain, in a way, the population in the same way. You have to do it based on small areas. You have to do it localized. That's really, really powerful. And as you will see, that actually is the reason why a lot of non-spatial models fail to describe a lot of, like this type of business models. It's really, really powerful. So summarizing, why spatial is spatial? This is kind of like a joke that we always make here. How many geographers have heard this? I mean, like we talk this a lot. Why generic tools do not work for spatial modeling? And this is the slide for your data scientists, or if you're a data scientist, use it. So essentially because of these two phenomena that I was describing. So if you don't take in consideration spatial modeling, if you don't use it, you're going to miss a very powerful spatial autocorrelation, right? You will miss that entire part, and you will also mean the second one that I explained, like the customers behave differently based on their location regional variation, which we call the data is non-stationary, the model is non-stationary. So those are two things. And if your model is not taking that into consideration, aka you're not doing spatial modeling, your model is not optimal. And in many cases, if your model is very, very heavy location dependent, it will be really, really wrong. So that's the idea in there. So how Carto can help us here? Here goes a little bit the pitch of like a selling point, right? So so most of these models, for those who are doing it, you will see this is a simplification. But I just want to describe, like to simplify the concept of like making a model, because it sounds so complicated, right? It sounds like like you have to be like almost a rocket scientist to make a model. It actually is not that hard. It requires like knowing a lot of the science behind it. It all starts with data. So if, for example, you're trying to predict what we were talking about before, the alarms, what is the probability that someone will buy an alarm, right? Let's say that that's the target column. Like you want to know what is the probability of that person, right? So you have historical data about that. You have like, if you are a company selling alarms, you know which customers in the past bought you, ended up buying, right? So you have your target column, as we call it, or feature. You have other data from the customer. How many times you contacted him, things like, like the marketing campaigns that you sent him, like whatever you've managed to collect from other points. So you have already kind of like information from the ones that you haven't yet, like sold, but also the ones that you've sold, that they might give you a lot of information. So that's your data. That's the data you have on your enterprise, on your company. Then you complement that with third-party data. And that's the beauty of location intelligence. We can essentially, if we know where your customers are, or your future customers, we can give you many more features, as we call it, many more columns on the database, by giving you data from Vodafone, MasterCard, and all the providers that you've heard. That's what we call data enrichment, data augmentation. That's your data. We augment it by understanding the area, right? And the last thing that we do is calculate what we call spatial lags. It's a little bit, like more complicated, but you call it the spatial correlations. Those curves that I was showing you about like the impact from one another, from one object to another, we can calculate that. Those are distances, like from, like to another customer, distance to the subway, like those are the influences of the space. And we put all those type of things together, that data, and then we put it to a process of modeling. There's a million more steps, so sorry, every data scientist here. It's not as simple. But, like essentially, you put it through modeling, you do a training, and essentially you end up with a function. With a function, simple more or less, that, essentially if you put the data behind it, it will tell you what is the likelihood of something. I mean, it will tell you the probability of the target. And also, in some cases, it will tell you what things were more important, to determine the calculation of the probability. So, once you get the model, once you get that function, essentially you use it for prediction and projection. So prediction, like I said, like give me what is the data, and I will tell you based on that model, what is the probability of selling to that customer. But also, it will tell you, if you go and do it in the entire Europe, it will tell you like for every place in Europe, what is the likelihood of customers to buy you. That's what we call projecting a model. And then you can use it to find hotspots, you can find it, like to see where you have more market potential and things like that. Really powerful stuff. So, I mean, a little bit the last thing, on this one. You've probably been bumped by, like machine learning, right? Everything is machine learning. Probably, linear regressions are the new machine learning too. So, but yeah, so you've heard, like machine learning a lot. And yeah, and it's really disrupting the world as we know it. Really is true. I mean, it's working incredibly well in many, many areas. You've heard a few of them, like in vision and video. You've seen, like how good is, Google now at detecting cuts in pictures, right? And other kind of like more creepy things. But yeah, so that's actually a whole area of machine learning. Then you have like natural language processing. So when you talk to Alexa, that's also called like machine learning applied to that. You got like general structured data modeling. So you've seen probably there's platforms that you push like credit card transactions, and it automatically and automatically find out what is the likelihood of being a fraudulent transaction or not. That's something that we call general structured data modeling. And there's also things like time-aware modeling that, like look at, like time series data. Well, now there's also one more, which is a spatial modeling, which unfortunately, or fortunately for Carto, there's not many platforms. In fact, actually, Carto is one of the few platforms out there that helps you to do this type of operations, or you're going to have to do it a lot with Python and a lot of tools on your own. So that's how is the context of it. Think of spatial modeling as another type of a specialized type of machine learning. Okay? So how do we help you with this? Essentially, the technology to run the models, the data that you need to do the data augmentation and the spatial lags, and expertise in case your teams do not have those capacities to build those models or require training, right? Those are the three things that we offer. And with that, I just want to finish again. It's time to move away from just visualizing data maps and start thinking about analyzing data using maps. That's the last thing really I would allow you guys to get out of the conference. This is the next step. And it's a very exciting one, and it brings a lot of new answers that we haven't seen maybe before. And hopefully this 101 session might have given you a little bit of an entry to that type of spatial modeling. Thank you very much.